This video is a summary video of P4, the second half of it, which is radioactivity. And this is going to focus predominantly on the core elements of this module, as opposed to the sort of additional content for triple. So this is specifically for combined science in the first instance. It's obviously relevant to triple, but there is more to be added on top of that. And I'm also not going to cover the very last section of this in a great deal of detail here, which is about energy levels and atoms. I'm going to cover the majority of this module, but I'm going to exclude that one section because it kind of sits a little bit separate. Okay, so the first really important thing that we have to get really clear in our mind about radioactivity is how it is different to radiation. Okay, so radioactivity, okay, is caused directly by the nucleus of an atom being unstable. Okay, so it's caused by an unstable nucleus. Okay, that phrase, unstable nucleus, is the first key phrase you should have in your mind, because it's an easy 1 mark that comes up in exam questions kind of all the time, right? So radioactivity is caused by an unstable nucleus. Now, the nucleus becomes unstable because inside the nucleus there are 2 competing forces. Inside the nucleus you have protons and neutrons, and the protons exert a repulsive electrical force, which is on the acting on all the particles in the other protons in the nucleus. What the neutrons do is they provide an attractive nuclear force called the attractive strong nuclear force, and those 2 forces try to cancel each other out. They try to balance each other out. You don't need to explain in your exam the detail of these 2 forces. You just need to understand that if the ratio of protons to neutrons in the nucleus is not correct, these 2 forces are not balanced, and that causes an unstable nucleus. So the key phrase you just need to use is in unstable nucleus. So different radioactive isotopes. So for example, carbon-12, okay, remember the top number is the mass number, bottom number is the proton number, or atomic number. Carbon-13 and carbon-14, okay, so these are 3 isotopes of carbon. They're all different forms of carbon. They all have 6 protons because that's what makes it carbon, but they have different numbers of neutrons, okay? So carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, carbon-14 has 8 neutrons, okay? Now, carbon-12 and carbon-13, okay, are stable, okay? Carbon-14, however, because of this imbalance between protons and neutrons being too great, that leads to the nucleus being unstable, okay? And so this is radioactive, and it's this specific isotope which is radioactive, okay? And whereas the others are stable, okay? So that's why radioactivity happens. Now, in order to try and address that instability, the nucleus then needs to try and recorrect the number of protons and neutrons in there. And the way that it does that is it emits radiation, okay? So be really, really clear and don't use the word radiation separately to, not separately. Don't use the word radiation as the same as radioactivity. Make sure you're really clear about how they're distinct. So radioactivity is just when the nucleus is unstable. Radiation is what is fired out, okay? So radiation is what is emitted from the nucleus, okay? It's what's fired out. And there are 3 types of nuclear radiation that we talk about, which is alpha, beta, and gamma. They each have a Greek letter because that's what they're named after. Effectively, they were called ABC, but in Greek, okay? Because when they were first discovered, we knew there were 3 basic types, and they just named them pretty arbitrarily, but just using the Greek alphabet, ABC, but that is alpha, beta, gamma, effectively is how they're named. So alpha is like this little fish symbol, B is like a slanty, beta is like a slanty B, and gamma is like a Y, like a stylish Y. Okay, so we'll come back to that in a minute when we talk about the 3 of them. But those are the 3 types of nuclear radiation. They come from the nucleus, and also they are all ionizing, okay? And understanding this idea of ionization is key, okay? Because all ionizing means is that when the nucleus is unstable and it fires out one of these three types of radiation, okay, these three types of ionizing radiation to try and make the nucleus more stable, in doing that, energy is transferred with these three types of radiation, and they are going to collide with other atoms. Now, when they collide with other atoms, they have a risk of knocking off electrons, okay? So ionizing, as a key word, just means, in the context of this topic in physics, is to knock off electrons. It means that the nuclear types of radiation have enough energy to knock off electrons from other atoms, okay? And there's one final point to kind of sort of tag in here. The reason that matters is if those electrons happen to be, say, for example, in a covalent bond holding your DNA together, it will cause damage to your DNA. So as a standard 2-mark question, one thing you can be asked is, well, why is radioactivity dangerous? Why is it bad? Why is radiation dangerous? And the answer to that is a 2-mark sort of point. The first is that if you are exposed to ionizing radiation, then that will damage your DNA. Okay, that's the first point. It damages your DNA because it knocks off electrons. That can cause damage to your DNA. And the second point is that could then potentially cause mutations or cause your cells to die. Okay, it's not going to kill you, so don't be that extreme in your exam. Don't say it will kill you, or don't say it will give you cancer. What you need to say is that damage to your DNA will cause damage to your cells. It may cause cells to die, and it may cause mutations, which may cause cancer. Okay, so it's not like 100% happens, but it is a contributing factor. Okay, so ionizing radiation, the three types of radiation fired out of a nucleus, are dangerous because they can damage our DNA, and then that subsequently can cause cells to die and cause mutations. So that's in terms of the difference between radioactivity, which is the cause, the unstable nucleus, and the ionizing radiation. If we just focus on radioactivity for a second, a couple of other points about radioactivity. So there are two key properties of radioactivity that you should be aware of, okay? The first is that radioactivity is random, which just means you can't predict when it's going to happen, okay? This graph, which shows the activity of a radioactive isotope being plotted over time, in reality doesn't look like this. The actual data would be like sort of a hairy sort of squiggly line, because it's not a smooth curve at all. There's always a little bit of random variation that happens. Okay, so if you were to count, like, say, background radiation, which is the radiation that always surrounds us, it's always there. If you were to count that every minute for 10 minutes, you'd get a different reading every single time. So whatever the background is, let's say, for example, it was 20 becquerels, okay? So the unit of activity, which you can see listed on the graph, BQ, is a becquerel. Okay, so a becquerel is the unit of activity. Let's say you measured 20 in a minute. Next time you do it another minute, it might be 21. Then it might be 18. Then it might be 22. It might be 20 again. It's just random, okay? You can't predict when it's going to happen. And the second point about radioactivity you should be aware of is it is spontaneous, okay? And that just means that you don't need to do anything to cause it to happen. Okay, now when we talk about radioactivity, it is important that you understand this idea of background radiation. Okay, background radiation is the radiation that is always there, it always surrounds us, perfectly natural, perfectly normal. And this little pie chart here shows the different sources of it. For the purposes of revision, I would encourage you to make sure you know at least 3. Okay, but you can see a large proportion of background radiation comes from radon gas, which is in rocks. Food and drink contributes quite a significant amount. Bananas, for example, contain a large amount of potassium, which is radioactive. And we notice that food and drink is important, but nobody panics about that. So it is perfectly normal, it's perfectly natural, as long as it's below safe levels. Okay. Buildings and the ground is a source of radioactivity, like the physical walls of the building. Because again, that's because of the trace amounts of elements like radon in the rocks that make up those buildings. Cosmic rays, which obviously come from space. Those are things like rays from the sun, but also more distant forms of radiation. Artificial sources, so things that are effectively man-made, then the next biggest proportion, but you can break that down into the biggest proportion of that, which is medical uses. So things like gamma knife for treating cancer, or even X-rays are ionizing, okay, but not radioactive, but gamma, so it's gamma predominantly for that. And then nuclear power and nuclear weapons you can see here, but they form a tiny bit, and often people remember these, but they are pretty insignificant in comparison to the others. So the big ones are cosmic rays, food and drink, and radon gas. I'd encourage you to probably remember those. But then medical uses like gamma knife, medical tracers, nuclear power, and nuclear weapons are also valid sources of background radiation. If you want to measure radioactivity, you want to measure background radiation, the device that we use to measure it is called a Geiger-Müller tube. And the Geiger-Müller tube will measure a number of radioactive counts, and what it will do is it will measure activity. Okay, activity is the name of the quantity that we use to measure radioactivity, and the unit, as we've said, is BQ, okay, the becquerel. And so on the graph, you'll very often get a graph that looks like this. It's activity against time. One additional thing we can do with radioactivity is, because it's random, if we want to measure it, we need to measure it in a way that is meaningful. And so one of the most meaningful measures, because it's random and it's always changing, is to measure the half-life, okay? So half-life can be defined a few different ways, okay? And there's three things you can use to define half-life. You can either say that it is the time taken for the activity to halve, okay? So option one is that it's the time for the activity to halve. As a substitute for activity, okay, another way you can define it is you could say it's the time for the number of nuclei to halve, or you could say that the count rate, if just a count rate was given off a Geiger-Müller tube, for example. So it's a time for any of those things to halve. So on my graph, for example, which is activity against time, my graph here is 8 times 10 to the 6th. So if I halve that, that's 4 times 10 to the minus 6. So what I do with a ruler is I mark off on my graph where 4 times 10 to the 6 is, which is obviously half of that. And then I come down and I measure what that is. And obviously you can see here in this case, that would be 700 seconds. So that means the half-life of this graph is 700. You should do this on your graph. You should draw it like this with a ruler, because that shows you the examiner, you know how to calculate it. You get a mark for that, and then you can get a mark for the answer. And if you can, like in this one, I can halve that again. So half of 4 is obviously 2. If I mark it again, I can come across and then come down, and you can see that is 1,400, but the key is that is another 700. So I can basically prove that it's staying constant, which is what it should do for radioactive decay. So it's 700, 700. So I can double check my answer effectively by doing that. So half-life is the time taken for either the activity or the number of nuclei or the count rate to halve when you're measuring radioactivity over time. And being able to identify it off a graph is one of the most common skills that you'll be asked to do in an exam. It's also just worth noting for a second that one skill that they occasionally will ask you to do in your exam is they will ask you to work out what the count rate is after a certain number of half-lives, okay? So let's just say, for argument's sake, right, that that we started off with a count rate of 2,000, okay? So that was the initial count rate, and I wanted to know what it would be after 4 half-lives, okay? So the way that I can do that is I simply need to halve it 4 times. So I can do divided by 2. I can then divide by 2 again, divided by 2 again, divided by 2 again. So I do that 4 times, and that would tell me what the count would be after 4 half-lives, okay? One way you might want to do that in your calculator is, if I've got my 2,000 as my initial count rate, I can do divided by 2, but then I can do it to a power, and I can do that power to 4, then it will give me my answer, okay? So I put the number of half-lives there. That's a quick way of doing it if you don't want to sort of just divide it. But they'll never do a huge number in your exam, so you can quite simply do this and just divide it by 2 again and again and again. They might ask you to work the other way. They might say, okay, the count is now 125. What was the initial 4 half-lives have passed? What was the initial count? And obviously you do the reverse, you times it by 2, and then you times it by 2 again, times it by 2 again, times it by 2 again, if you're doing it for 4, and you get back to your original number. You can do the same thing. You could do 1.25 times 2 to the power of 4, and that would also give you the same answer. Okay, so just be aware that's one other skill they might ask you to do with half-life in your exam. Okay, so we have the basics of radioactivity and we have the basics of half-life that we've kind of talked about there. So now let's focus our attention on one of the main bits of this topic, which is about comparing our 3 types of ionizing radiation: alpha, beta, and gamma. Okay, so you need to know pretty similar things for all of them. Okay, so we're going to do these in conjunction. Right, so the first thing that you need to know about all of them is what is their nature. Okay, this throws people in your exam, because people get confused by what does it mean by nature. Nature is just a fancy way of saying what is it, like what actually is it. Okay, so an alpha particle is a helium nucleus. Okay, that's what it's actually made of, and that means you can see in this diagram it's made of 2 protons and 2 neutrons. Okay, that's what it's actually is. It's what it consists of. So when we say it's nature, that's all we're talking about. What is it? Beta, in comparison, is a high energy electron. So a beta particle is just an electron, but it's a high energy one. Okay, it's a high energy one that's been fired out of the nucleus. And gamma radiation is an electromagnetic wave, because gamma, you will remember, is one part of the electromagnetic spectrum. Okay, so and it is the highest energy electromagnetic wave, and it's the highest frequency. It's also got the shortest wavelength, and that crosses over with the other part of P4, which is waves. Okay, so that's the nature, that's what each one is. Okay, so once you understand the nature, you can then start to say a few other things about it. So the charge, remember the symbol for charge is Q. Okay, the charge on an alpha particle is +2. The reason being it's made of 2 protons and 2 neutrons. Protons have a charge of +1. Neutrons are neutral, they have no charge, and so since there's 2 protons there, the overall charge is +2. The charge on a beta particle is -1 because it's an electron, so it's the same as a normal charge on an electron. And the charge on gamma is 0 because it is a wave. Okay. In addition to that, you can also comment on the mass. The mass of an alpha particle is 4 because it's made of 2 protons and 2 neutrons. Added together, that gives you a mass of 4. Now, in comparison, the beta particle has a mass of 0.005 U, which is basically 2,000 times smaller than the proton. If you're comparing these two numbers, the important thing for you to realise is in comparison to each other, the alpha particle has a large mass, the beta particle has a small mass, and in comparison to gamma, remember gamma is a wave, mass of gamma is effectively 0, okay? It's negligible, okay? We can basically ignore it entirely. So the point is, alpha is large, beta is small, gamma is non-existent in terms of mass. If you just compare alpha and beta, alpha is 8,000 times bigger than a beta particle. The important reason that mass idea matters is if you combine that and the charge, you then get one of the most important properties of each of the things, which is how ionizing each of these things are. And so alpha is the most ionizing type of radiation. Remember, ionizing means to knock off electrons. Alpha is the best at knocking off electrons. The reason being, it's got the biggest mass and the biggest charge. Biggest mass and biggest charge. Beta is moderate at ionizing because it still has a reasonable charge and it still has a mass. Gamma is the least ionizing. Okay, it's the least ionizing of the 3 because it has no charge and no mass. Now, another property works in kind of conjunction with how ionizing it is, okay, and that is penetration, okay? So alpha is the least penetrating of the 3 types of radiation, which means it's the easiest to stop, okay? In contrast, gamma is the most penetrating, okay? It's really difficult to stop gamma, okay? So one thing that you need to be really clear about for each of these is what will stop them. What will stop each of these things? So for alpha, you need to know there are 3 things that will stop alpha. okay? The first is 1 to 2 centimetres of air, skin, and paper, okay? That means that outside of your body, alpha is pretty safe because it can't penetrate your skin, okay? It can't go through there, so that's pretty helpful. But inside your body, it would be really damaging because it's the most ionizing. So the famous example of that is this Russian spy, Alexander Litvinenko, who was poisoned with polonium-210, which was an alpha emitter, because he'd ingested that. And remember, if you ingest it, that's contamination. So contamination is when a radioactive source is either on your skin or inside your body. So you're in physical contact with the radioactive source, as opposed to irradiation, which is just when you're exposed to the ionizing radiation, you're not in direct contact with the radioactive source. So Litvinenko was contaminated. He ingested polonium, and that then slowly killed him. And it did that by alpha being highly ionizing, knocking off the electrons in his DNA, which caused damage to his cells. His cells then died. That then caused organ failure, and so he slowly sort of died that way. A very slow and painful way to die. So skin will stop it, but so outside alpha is safe, inside your body would cause a lot of harm. It won't pass through paper, or very a small amount of paper will stop it, and it doesn't get very far in air. Okay, now beta, okay, the two things that will stop beta is air again, but 10 to 15 centimeters of air will be enough to stop beta, so it will go a bit further than alpha because it's more penetrating, and a few millimeters of aluminium. Okay, so aluminium will stop beta more than a few millimeters, and but beta would be quite happy passing through skin or paper. So one of the uses, which I'm just going to mention at this stage, of beta is that it's used in paper thickness. Okay, and so you should be aware of the uses of each of these types of radiation, because often they are the context of exam questions. So the most common one, bar none, is they ask you about paper thickness factories, and the reason being that alpha wouldn't pass through paper, so you couldn't use alpha for that, but you can use beta because it will pass through paper but will be affected depending on the thickness. Okay, gamma, on the other hand, because that's the most penetrating, will all pass through the paper, so you wouldn't notice any difference there. So that then brings us to the two things that will stop gamma, which is a few meters of concrete or a few inches of lead. You may think, why lead? Seems like an odd choice, but basically lead is the last element on the periodic table, the biggest element on the periodic table that's not radioactive. So effectively it's like the biggest shield you can do without using something that's already going to increase your amount of radioactivity. That's why lead, okay? It's the biggest atoms kind of to block the radiation effectively. So just following on from that, so you need to know what will stop each type. Remember, gamma will pass completely through all of these things, okay? It will only be stopped by these. The other uses I just want to mention very briefly for alpha particles, the use is that they are used in smoke detectors because they will ionize the air in the smoke detector, and that allows a current to flow. And if smoke particles enter the smoke detector, that will block the flow of current, reduce the current, and that's what triggers the alarm. Beta is used in paper thickness, and gamma is used in medical tracers and cancer treatment. It's also used to sterilize medical equipment, and it can also be used in other types of tracers like industrial tracers as well. That brings us to pretty much the last thing on this, which is nuclear equations, okay? So for nuclear equations, these will never change. They're always going to be the same process. You just need to represent how an isotope can decay via one of these three types, okay, and show that in an equation. So we always have, remember, the mass number is the large number at the top and the atomic number is the small number at the bottom. So for example, if I had uranium-238 as an example, and uranium-238 will have an atomic number of 92, you will not be asked in a physics exam to name the element. All you will be asked to do is fill in the numbers here, okay? So what would happen if uranium decayed via alpha is it would turn into thorium. As I said, you're not going to ever be asked to know that. You'll be told that, What you will be asked to do is to say, okay, well, what is the number here and what is the number there? Okay, so the key thing to remember is alpha is always 4 and 2. That will never change. Okay, so alpha is always 4, 2 because it's made of 2 protons and 2 neutrons. Okay, so the 2 is the number of protons, the 4 is the combined mass number, 2 protons plus 2 neutrons. So what happens to this number? Okay, the top number, the mass number in alpha always goes down by 4, and the atomic number goes down by 2, because the numbers on the left have to add up to the numbers on the right. So 92 is made from 2 plus 90, and 238 minus 4 would be 234. So in alpha decay, always the top number goes down by, the mass number, the top number goes down by 4, the atomic number goes down by 2. In beta decay, so for example, carbon-14 will undergo beta decay. What happens then, and this is one key fact you need to add into your understanding of beta, is that when beta occurs, a neutron turns into a proton and the beta particle, which is obviously an electron. Because what you should think when I said that beta was a high energy electron, you should have been a little bit suspicious, because I'm saying this comes from the nucleus, but you should know that the only particles inside the nucleus are protons and neutrons. So the question is, if this electron is coming from the nucleus, where does it come from? And so what happens in beta decay is one of the neutrons breaks apart, it decays into a proton and a beta particle, which is the electron. So because of that, the total number of protons and neutrons hasn't changed. Okay, you've turned a neutron into a proton, but the total number is still the same. So the mass number stays exactly the same. Okay, it's unchanged. Okay, so no change to the mass number. The number of protons, however, is increased by 1, so that would go up to 7. And so that's always going to be the same, it's always going to go up by 1. So in that case, that would be nitrogen. Remember, you're not going to be asked to know that, you'll be told it. And just like we did with alpha, beta is always written the same way. It's always 0 and minus 1. And I could write it as the B symbol for beta, or I could write it as an E for an electron. Both is fine, but that bit won't change. Lastly, I'm just going to mention gamma. I didn't think they'd ever ask this as a question, but they have. What's the equation for gamma? And the reason for that is when gamma occurs, what happens is the nucleus changes shape. Okay, that's what actually causes the gamma radiation to be emitted. And so there's no actual change to the nucleus, it's just changing shape. So in the case of gamma, so for example, if I use uranium again, so 238, we can show the uranium in an excited state with this little star, but the numbers, when you do the nuclear equation, will be exactly the same. And believe it or not, that's been a 2-mark question before, okay? Because some people panic and start making up what happens to the numbers, right? But in reality, gamma, there's no change to the nucleus, it just changes shape, so the numbers are identical. So that is our summary of the key points of radioactivity in P4. So it's really important you know the basics of radioactivity caused by an unstable nucleus, it's random and it's spontaneous. We have background radiation, and we have how do we calculate half-life, and we know the definitions for that, so the time taken for the activity to halve or the time taken for the nuclei to halve. And then we have the detail of our 3 types of ionizing radiation, alpha, beta and gamma. Remember, X-rays are also ionizing, but they're not nuclear, okay? And we need to be able to compare these and understand what will stop each one, which one is most ionizing, etc. Okay, and then turn that into nuclear equations. So if any part of this video hasn't made sense, please go back and rewatch it, because this is always a big part of your exam, so it pays to make sure you know this information really well.